Release a spherical iron in oil. The object is acted by three forces: downward force of W, the buoyancy force when it's sinking. Buoyancy force is not that big, so it can't cancel the weight, and the drag force, the viscous force. You know that the viscous force at the beginning when the object starts moving has no very considerable value. But as the object is speeding up, the drag force is getting larger and larger. And finally, these two forces can cancel the weight and object will be in terminal speed. This video is about how to find that terminal speed. So let's start from the beginning. In previous videos, I explained for a spherical object in the liquid, moving in liquid, the drag force or the viscous force is going to be 6 pi eta RV. Eta is the viscosity, r is the radius of this sphere, and v is the speed. I told you the drag force is not constant and is highly affected by speed. The other is the buoyancy force, which is equal to the weight of the displaced liquid. Here I have density of the fluid, the volume of the object because it's fully submerged, so the volume of the object is equal to the volume of the displaced liquid, and finally the gravitational acceleration. The last is the downward force of W, mg. Let's take the density of the sphere to be rho s. So it's mass of the object divided by the volume. So mass of the object seems to be rho s v. Let's substitute that. Now I will find the net force. At the beginning, I suppose that W is larger than some of these two forces. So the net force is downward and it's going to be, let's say, F net is W minus Ft plus Fb. Okay? And then I plug in the values like that. These are the two opposing forces. What if the object is in terminal speed? In terminal speed, we expect the drag force to be so large that can add up to this and cancel the weight. So I expect the net force to be 0. If I take it like that, I factorize from Vg, the common term here, and then I can find the terminal speed, the maximum speed of the object like that. Here I have subtraction of the two densities and volume of the object and gravitational acceleration. Downstairs you see 6 pi eta, the viscosity and the radius. You don't have to memorize this formula. Just keep in mind that basically how the three forces are fighting with each other and find the final speed for you. Is it always the same case? No, I should tell you something very important. Sometimes the object, rather than sinking down, is acted by a very, very large buoyancy force. Let's say by force I push a football to a swimming pool and then release that. Basically, it's acted by a very large buoyancy force. W is not that big. And so the object starts moving upward. So the motion is upward. Now it's acted by also the drag force, which is now helping W. And so here, F net at the beginning of the motion will be the buoyancy force minus W minus Ft. Here it's as practice, you can find the terminal speed. But let's consider a question which is exactly explaining this case when the object is moving up and the buoyancy force is very large. This is why I told you, you don't have to memorize that formula. Just learn how to work with those terms. A ball of radius 8 millimeter and mass of 1.3 gram is released from rest from the bottom of a long vertical tube filled with oil. The ball raises toward the surface of the oil. As you see, now the ball is moving upward. So the buoyancy force is very large, W, and the drag force here are downward and against the buoyancy force. The diagram shows how vertical speed of the ball varies with time. You see at the beginning there is no speed. The speed is getting larger, larger, and finally a terminal speed, as expected. Keep in mind, object is moving upward. Buoyancy force is larger than W and Ft at the beginning. Finally, Ft will be large, and then these two will cancel the buoyancy force. The case is motion upward. Okay, part A, estimate the initial acceleration of the ball. Initial acceleration means the slope of the vt graph at t equals 0. According to kinematics, we know that the slope of a vt graph is acceleration. So let's draw a tangent line. Estimately, this is the tangent line at t equals 0, and establish a right triangle here. This right triangle has a slope, and the slope is the slope of graph at t equals 0. Here I take the height to be estimately 1.5, and here I have 0.35, and so acceleration is 1.5 divided by 0.35, height over base. It's almost 4.3 meter per second square. Part B, hence calculate the magnitude of the buoyancy force on the ball at t equals 0. At t equals 0, you know guys, there is no speed, so no drag force. Forget about drag force. We have no drag force here. We have just buoyancy force and W. Which one is larger? Yeah, necessarily the buoyancy force. The object is moving upward. So F net, according to the Newton's second law, will be FB minus W, and we can put it equal to MA. Here is the approach for finding the magnitude of the buoyancy force. FB minus W is equal to MA. Let's plug in the values. Weight is density of the object, volume of the object times G, or if you have the mass, mg. It's easier. G is here, mass is given to be 1.3 grams, so it's 1.3 times 10 to negative 3. Right side again, mass is the same, and acceleration is something we already found, 4.3. Just make a calculation and find the buoyancy force to be 1.8, 10 to negative 2. Part C, draw a free body diagram for the ball at time of 1.5 second. 1.5 second means that the object is almost at its terminal speed. So we prefer to have F net to be 0. So let's draw the free body diagram. This point is a representative for the object. Now the three forces, upward force of Fb and the two opposing forces of W and the drag force. We draw them to a scale as they add up to cancel the buoyancy force. Part D, determine the coefficient of viscosity of the oil. Okay, first of all, at terminal speed is the best point to find it. Why? Because at terminal speed, F net is equal to 0. Okay, what the F net is, Fb minus Fd minus W is equal to 0. So let's write it in this way and take the Fd on the right side. The reason we are looking for the viscosity, and so it is hidden in Fd. Then I substitute the values. Fb is something we already found it, and it's always the same even if the object has larger speed, not only at t equals 0, but all along the motion Fb is the same. Here is mg. Mass of the object was given to be 1.3 gram, so it's multiplied by 10 to negative 3 to be in SI units. Right side is the drag force, 6 pi eta, it's our goal, radius, and the terminal speed. Terminal speed is obtained from the graph to be 1.15 almost. The radius was given to be 8 millimeters in the question, so 8 times 10 to negative 3 just remains a short calculation, and you will find the viscosity to be 3.4 10 to negative 2 pascals. You know the viscosity has the unit of pressure. Okay, we are done. Thank you very much. Thank you for being with me and your attention to this video. See you very soon.